Okay, I want to talk a little more about ideals. This is where we were. We defined in particular this thing called a principal ideal. I guess I'll only talk about principal ideal when I'm in a commutative ring, so let me just change this a little bit. An ideal I in a commutative ring. Ring R is called principal. I said that kind of here, that if R is commutative, but it's called principal if I is of the form circle A. By that we mean all multiples of A for some A in R. Okay. Here's an example. 3 times Z is a principal ideal in Z. This is all multiples of 3. Because if you add two multiples of 3, you again get a multiple of 3. Negative of a multiple of 3 is again a multiple of 3. Multiply 2 multiples of 3, you again get a multiple of 3. So multiples of 3 form a subring. But it's more. If you take a multiple of 3 and multiply it with any integer whatsoever, what you got is still a multiple of 3. And that's sort of the key condition for being an ideal, you see. If you take an element of the ideal and multiply it with any element of the ring, the product is still in the ideal. And 3 times Z certainly has that property. Okay, so we had this lemma which said that the only kind of ideals in Z are these, multiples of a particular number. And only kind of ideals in polynomial ring in one variable are also just these, multiples of a particular polynomial. Things like x squared plus 1 times fx, which means all multiples of x squared plus 1. Yeah. I don't know why I'm writing in red. So I want to argue this out and talk a little more about ideals. Let me make some space here. Before proving this lemma, let me tell you how to make some new ideals given some ideals already. If you give me some ideals, I can make some new ideals by applying certain operations. So that's one nice thing about them, that there are lots of things you can do to them to cook up new ideals. Let's get rid of this. Make some space. Okay, so let's call this operations on ideals. Okay. So first of all, intersections of ideals are ideals. So if you give me a bunch of ideals, I can intersect them all, and the intersection will again be an ideal. So that's the intersection. That's the first operation of a family of ideals in R is again an ideal. So what that allows you to do is that if you give me any subset of the ring R, so before we begin, maybe we should say let R be a ring. So what this intersection business allows me to do is that if you give me any subset of the ring, I can form the ideal generated by that subset. So let me explain. Let S be any subset of R. It's a non-empty. Non-empty subset of R. There is an ideal that contains S. R itself is an ideal that contains S. So I can take all the ideals that contain S and intersect them all, and that would again be an ideal by this. So that's going to be the smallest ideal that contains S, and I'm going to call that the ideal generated by S. Then the intersection of all ideals containing S is again my writing is sort of degenerating. Containing S is the smallest ideal containing S and is denoted by angle bracket S. So if S is x1, x2, xn, just a finite number of elements of S, then verify that the ideal generated by them, which we should really denote like this, right, putting an angle bracket around it, but we won't, that looks sort of weird, a parenthesis and then an angle bracket, so we'll remove the parenthesis. Then we'll just denote the ideal like this, consists of, you take these guys, x1, x2, xn, multiply them by arbitrary elements of the ring, and add them up. So in linear algebra, what you would call all linear combinations of these elements. So you take these elements of the ring, multiply with arbitrary elements of the, you must take x1, x2, xn, multiply by arbitrary elements of the ring, and add them up. All such things form an ideal, and that's the smallest ideal that contains x1, x2, xn. Okay. So if you give me a bunch of ideals, if you give me a bunch of elements of any ring, I can consider this ideal. So in particular, for example, in Z, a priori, you have other ideals. In Z, we could consider this ideal. The ideal generated by, let's say 24, 36, and 54. This means the smallest ideal that in Z that contains these three numbers. Practically, which means you take any multiple of 24 plus any multiple of 36 plus any multiple of 54. All such things. All integers that look like this. I write this down to show you that this lemma here has some content, you see. This a priori does not look like any of these ideals. But it has to be one of them because that's what the lemma is saying. The lemma is saying that all the ideals in Z are just these guys. Multiples of 2, multiples of 3, multiples of 4, etc. This one doesn't look like one of them, but it is in fact. Can you tell me which one it is? Maybe we'll answer that next time.